small time delay. I cannot click on that.
It's done.
No, no. I just lost my cursor. Escape. No, got it. Got it. Oh, okay. I think it works. So all sources are variable, astronomical sources and sources on Earth as well. And I put this arbitrary time scales for variability: short, less than 100 years, and long time scales more than 1,000 years. But this division is arbitrary, really, because you have sources which vary on millisecond time scales. We know that there are these outbursts, very, very fast outbursts on very short time scales, measurable, so we can measure those. But there are also these long-term events which contribute to the trends, which we'll see. Long time scales, more than 1,000 years, means the sources evolved and they change from, small star to the big star to the black hole, or the galaxy from, we don't know how it starts, but maybe from the small black holes you have mergers of different systems, and you, in million years, giga years, you generate the universe which we have.
Do you mean the lifespan of the source, or you mean?
Yes. So some lifespan of the source could be very long, right? So you can have a galaxies like Milky Way lives very long, and you have generations of stars in the systems. So you have stars which last, 10 million years, giga year, billion year. So very long, but we don't observe these systems as variable. We can look at the population and determine that there was population of stars which were born million years ago, or 10 million years ago, or billion years ago. But we cannot look at the evolution on that scale, right? What we can see is the variability which we can detect on these short time scales, like minutes, nanoseconds, days, years, etc. And given these time scales, you can look at different processes which generate these variations. So they may not contribute to the full evolution of a star, or in some ways they could, because when we see the outburst of a star, we can maybe predict what happens later, or we can sometimes see the remnant of that outburst in terms of a supernova. So we can observe some of those sources on the shorter timescales. So supernova 1980A was exploded in 1987, and we can still look at the remnant and determine the evolution of the ejecta of that supernova over the last 30, 40 years, right? So we have also different type of variability in the systems. Ina, can you moderate the chat, because I see that there are some. Okay. Okay.
And so far there is jokes.
Oh, which I cannot see. All right. So variability. I mean, there are different type of variations, of course. Periodic, we know what periodicity means, and some sources or systems are periodic because of the orbital motion of the system, right? The binary systems are periodic pulsations on the star. So you have periodic variability, which gives you a time scale for periodicity, which is characteristic of this periodic signal being generated. There is also stochastic variations, which we don't necessarily model. We just have the stochastic changes in the flux or intensity of the source. And the stochasticity means that maybe there is no corresponding timescale, or maybe there is a characteristic timescale of this process which drives the stochastic variations. We also have flaring variability, which means the source is quiet, and at some point there is a huge flare, huge change in intensity of that source. And the sun has, of course, flaring events, which we know and observe, and we can see the result of the sun flares, because the radiation comes from the sun and hits the Earth's magnetosphere, and we see the effects of those. there is quasi-periodic variability also in certain systems, which is important for studying the, for example, accretion dynamics or other dynamics which cause the quasi-periodicity. We can look at the systems which dim, so change this scale or brighten. And there are other types. There is also, the change in the intensity due to absorption. So something is goes across the source, which emits quasi-stationary emission. So there is all sorts of variations, and the sky is not constant. So if you look at the optical light and you look at the sky, it seems like, oh, nothing is variable, really. But when you start looking at the data, you see that there is plenty of variations which we can use. We can use as a probe of the physics and astrophysics. Yes, so now the next slide doesn't want to go. Okay, let's see it here. Return, no. Oh, technical difficulties. Let's. What?
Command that. It doesn't matter. Yeah. Command that, but they do it in Keynote.
Command tab. No. I don't know. Oh yeah, I have to be in Keynote for some reason. It's frozen. Pause. Pause. No. See, because I'm on this screen, sorry, I'm not on my screen. Stop share. Well,
If you do command tab, they do it in Keynote.
I'm trying to do it. Command tab. No.
Hold down command and then tab.
No. I think I'm like stuck here. I do escape and I cannot get remote control apps more. I'm on that bar. I can do pause share. What does this mean? Let's see if this. Okay.
I'm glad to see though that wasn't too bad that I forgot how to get here.
Well, so
I can still catch up with that.
This is a demonstration what time delay means.
I know, and now we have this artificial time delay.
2019.
So I'm really in this. I don't know. My computer is Vinay. I just don't know what's happening to my computer. Yeah, you can try, but it's like it's frozen. Doesn't work. Doesn't work. Any of the keys, and my bar is there.
Click.
What?
Just click on the.
Oh yeah. Okay. Resume share. No, this didn't work. So this works. Okay, but now how we go back? Okay. Anyway. Oh yeah. I can use this. All right. Sorry, guys. Oh no, but we are too far. I'm still not in the right slide. Pause share. This is not great technical difficulties. Stop share. No. How do you go back? I think this, yeah. I don't know, for some reason the computer is delaying things. Okay, now I have to do resume share. Okay. So in time delay, I sort of separated this into two different types, where we have reverberation, which means the primary radiation is reflected from the medium and could be reflected and reprocessed by some medium surrounding the source, which causes the echo, and we see that echo, observe that echo. And we can also have the enhanced emission where the waves propagate through the medium. And then the next sort of like category will be light bending, which is related to gravitational lensing, and delay variations, which we can observe between gravitationally lensed images. Now I'm going back. No. Sorry, that's like, it never happened. I never did this. Okay, now this working, okay. So reverberation, so primary radiation. So I have an example. Let's see if this works.
Your
Of-
screen sharing is paused.
Oh, okay. So reverberation, when the primary radiation is reflected or reprocessed by the medium, it's often used in astronomy. And
The game is paused.
I don't know.
I think this is because you're sharing the window and not the screen,
Oh, yeah, yeah.
because then it will pause once
Yeah.
you change the window. But
Oh,
you could just stop share for a second
stop share.
and then share again and then just choose your screen.
You know, this is too complicated. Okay, and now I can share.
This will share.
And now I have to go to Zoom and share. Share screen.
Yeah, just
That,
share.
that one, share. Okay. So this is the page which was this. I mean, it's a strong page. There was a campaign to actually look at this reverberation data, light curves in one of the active galactic nuclei, and on that website we have this example of what happens where you have this emission in the lower panel, which is the continuum emission. So this is the primary emission from the source, and it reflects a change in the line emission, which is up here. So you can see that the little variations impact this line. This is the emission line in that system. And sort of the measurements of the delays between the line and the continuum can be used in this case to measure the black hole mass, for example.
So the peak is the line?
This is the line emission, right? You can see this is 1450 up to 1700 angstrom. So this is the line that this is AGN, so you've got also some absorption, which is associated with the line on that side. And continuum flux comes from UV, and this is the HST, and that's carbon 4 line in the NGC 5548.
Obviously, yeah, it's difficult to make out from that spectrum. Is the ratio of line to continuum changing this, or is everything is going up and down?
It changes. So the profile of the line, the width of the line, and the centroid of the line could change. The intensity of the line, so equivalent widths will change because there is a response between the continuum. Continuum illuminates the clouds, and depending on the photoionization of the clouds, which is related to the intensity of the continuum, you will have the variability in the line profile. Right? So it will be intensity of the line, the observed width of the line, perhaps, and the exact response function, which is related to the property of the medium and the intensity of flux illuminating the medium, is part of the modeling of this system. And the campaign was very successful, and actually I will show, if I can, in a minute, the graphs. Let's see here. Where's my talk? Now I lost my talk. Google. Where is my talk? Did I close my keynote? Oh, okay, I'll go back to my keynote. Where is my keynote? Here. I think it's under this Window. Oh, maybe under Google. It's my new slide. Sorry. Anyway, okay. I stopped. Did I stop the share? I think I did. Okay. All right. So I can do the share again. I think that's what I needed to do. And go back to Zoom. Okay. I think we will see this now. Zoom share. Let's see. I can stop share. I have to stop share. Where is screen share? But I can see, sorry, I still can, oh, there it is. Okay. All right, share. Play. Okay, this will be difficult because I had few slides. So anyway, the reverberation mapping. So this example of reverberation allows us to look inside the systems which we cannot resolve. So in the case of active galactic nuclei, we're looking at the very central region of the galaxy, which emits this intense UV radiation. So we can look at the structures into unresolved structures of this AGN, which are smaller than 1 parsec. So it's like 3 light time size. And we can also use these measurements to measure black hole mass, where mass is related to emission line width and the time delay between the continuum source and the region which emits the lines. And
is the mass proportional to the time delay?
Because the systems are, I'm echoing, because depending on the location of the clouds move around, and depending on the intensity which we generate, the clouds can be closer or higher, and intensity depends on the accretion rate, which generates the emission, and accretion rate and black hole mass are linked together. So you have the system in which you generate the UV radiation, which illuminates the clouds, and depending on the mass, the clouds are closer or farther away. And the line width depends on the orbital motions of the clouds. So that's the assumption, that's the picture which we have in mind. So in this, well, there is no clouds in that system over there. There is broad line region highlighted in the sketch of the central region. And in broad line region could be closer or farther out depending on the mass of the black hole. And this is the picture which we sort of have in mind when we think about unresolved structures in the center of the galaxies. And there is a black hole which we don't typically observe directly. We only observe the light which is emitted by the material close to the black hole. So you've got the accretion disk, which is typically the material surrounding the black hole, and because of the heat, it emits radiation. There is corona, very hot, medium above the accretion disk, broad line region, and this dusty torus, which is mostly responsible for infrared. And in the panels below, you can see the light curves in different bands, which probe different parts of that structure. You've got X-rays in blue, which is corona jet. This little arrow shows jets in some systems. There is UV emission, which is related to disk and corona, and also H beta, which is the line emission from the broad line region, and then the dust is in the infrared. So all these light curves, when you analyze them in a consistent way, will result in understanding what's the structure, distances, the location of different emitters, etc. And this is not an easy problem because you have to observe the source for many, many days in this case, and with different telescopes. So there are measurements problems, and you have to take into account all the calibrations between different types of instruments. And the group which designed the storm campaign did very good job. So they really calibrated the data, and they actually released the data on that website which I was showing. So if somebody is interested in tackling the problem. The data is available. The standard methodology which was used in this campaign to determine the time delays was related to autocorrelation functions, typically, which is often done in this case. Okay, this works. So now this is the next type of observations related to the echo are slightly different, and in this case, this is the explosion of the star, and the shock waves propagate through the medium. This enhancement of the emission, which is going through the interstellar galactic medium, and you can observe actually in X-rays these rings. So this is sonization of this.
So the sun is some artistic.
Yes. So there is a project at Chandra that sort of makes the observations visible to people who cannot see. So so sonification. So this was example of this outburst. And then we also have observed the light echoes in the galactic center, and this is the example from the Chandra press release image where our galactic center is here, and in these two clumps highlighted on two sides, we have it was determined that there were changes to the morphology of this emission. And the morphology of the emission changes was telling us about the response to the outbursts in the center of the galaxy, which caused the echo, similar to the one on in the star, which I was showing you above. So these are different analyses, because here you look at the properties of the medium and analysis of the medium to understand the maybe the timescales as well, and go back to the original explosion, in this case in the galactic center, to determine the age in which happened, because this was probably like a few hundred years ago. It wasn't now, right? In case of the star, the explosion was actually observed. I don't know if this was the system when we observed it, and then you could see the propagation of the wave through the interstellar medium. It's different time scale. Okay, I'm going back. Okay, we're going in different direction again. Eventually I'll get to, I'm telling you, this is not in, okay, we're getting to gravitational lensing. So this is the probe of big scales and big structures in the universe. And I wanted to show you the image of this strong gravity which bends light. So in this image, we have the cluster in front of the strong lens is a galaxy cluster, and you have these arcs which show the lensed galaxies. So this is very complex image where you have a lot of galaxies which don't look like a galaxy. They basically look like arcs because of this strong gravity in the cluster. So what we were looking at was also the images of very distant sources. So the cluster, so the quasars which are far away can be lensed by the galaxy or cluster of galaxies, but the galaxy, and the galaxy, this lens will cause the multiple images to be visible. So there are the examples of different systems where we have 4 images with the central image as this is the lensed galaxy, and that's a very nice system. This is again lensed galaxies and system. These are slightly more complex where you have lenses. So quasar images lensed and the galaxy, another quasar image. So these are quadruple lenses. And this is
are those real images?
Yes, these are the HST images.
Those are fantastic.
Yes, there is a lot of fantastic images like this, David. And yeah, so
I thought it was only Tox cartoons that looked that nice.
No, there
Sorry.
there are real images in different wavelengths, and this is HST. There are images in radio and in X-rays. So in Chandra, on the right side, you see the lens which is observed by Chandra, and it's resolved. So you have this little four sort of images of the quasar, and this illustration shows you how it happens. So you have galaxy, the big galaxy between Chandra and the quasar, and then these images are formed because the light from each from the quasar is banded around the lens like this, right?
Yeah, the bending must be like the picture has an angle. It must be an arc.
Yeah, I guess this is the simplification, because the angle which is there is actually used in modeling the whole system and the lens itself. So I think it's typical to use just the angle, not the light.
Because the left to right is so compressed.
Yeah, maybe
The
also
scale,
too.
the distance between Chandra and the core is the same, meaning also the magnitude of the
Yeah,
lens. So
yeah.
Yeah, it's what we call the thin lens approximation.
That's right.
But is that mathematically that curve is well understood? Can be described by some equation, like from harnessing bands?
I don't think probably I don't.
If you know the distribution
Yeah.
of the lens mask, yes.
Yes,
You
but
typically don't, and so you assume that's a point mask, and so the error is probably in assuming it's a point mask and it's not.
But also, yeah, there is complex model of the lens itself, right? And so we never looked at that, but there is recent development in that area where you've got very good images, and you look at the, there's approximation of the mass distribution. So, typically you have spherical mass distribution, but they do modified, depending on precise location of the images, you can determine the model of the lens, so distribution of the mass and gravity in the lens. It's not fully deterministic, so the modeling is multimodal, I would say. That's probably it's not exact. And
So
there's a lot of uncertainties in that.
If you have some estimate of the curve, you can inference the mass itself.
Yeah, I guess that's what happens, because you have to, you get all this line of sight effects, and depending on how this bends, you can go and measure. There is a lot of question in measuring the lens, and I'm not near even understanding what goes into modeling the lens. But there is Francois Lanous, who was doing recently some nice statistical modeling, so maybe we can ask him to present at some point. It will be interesting to see, because there is a lot of uncertainty in the distribution of the mass, even in these images. They are very, so the light, even from the lensed galaxy, is not well known how it's distributed. So to measure the lens, you need to go there. So it's a lot of questions, actually interesting questions.
Sorry, could I interrupt with a?
Yes, Jeff.
It's pretty much following up what you were just saying about modeling the lens and getting information about the distribution of the mass in the lens. But what I find really fascinating is kind of the other end of that, other side of that coin. In the modeling, you also get a picture of what the source would look like if the lensing was kind of inverted. So in a way, you can think of this as a huge telescope that has some aberrations in it, but you can correct for those aberrations and construct an image of distant regions of the universe. It's really incredible potential for exploring the detail, especially with JWST images, which of course are even better for this than Hubble. I haven't kept up with what the progress on that is. I know it's the modeling, the mathematical modeling is complicated, as you said, because of uncertainties and how to really picture the distribution of mass in the lens. But I think this is really a great field for future research, and people interested in image deconvolution and correcting for aberrations and so on should have a field day with this business. But anyway, thanks.
Thanks for coming. Yeah. So yes. So actually, this. So sorry.
That's an interesting comment. Like,
Yeah.
meaning, I mean, it's like it's the kind of thing we're trying to do with PSF uncertainties. I mean, in this case, the PSF is less.
Yes. So there is. I mean, I think this is the article which recent review. Oh, it's 2022. Sorry, the Astronomy Astrophysics Review. It's not 2020. It's 2022 paper where they reviewed the problems. Where we are. So it's basically status of the strong lensing time delay cosmography in this era, because it will be, as we already have, many lenses, but there will be more. And Gaia new release just announced 300 more lenses. So there will be more lenses with LSST, which is coming on board, and more data. And the question will be, can we do sort of the analysis of those lenses? The question is why, right? Why would you do that? And this is why. One reason is that you can measure the sort of scales in the universe, and if universe is large and Hubble constant is low, we will have large time delays, as illustrated on the top panel. When universe is small, we have high Hubble constant and small time delays. So this is basically like the trivial description of what it is, because at the end, getting this value of Hubble constant, which provides the scale, is not trivial. It requires understanding of the time delay, understanding of the lens, and all the other details which go into measuring the Hubble constant or measuring time delay. So we focused only on time delay in the past with CHASC and Antoine Meyer and David Van Dyke and people here, Johnny and Vinet, and Casey Mandel, of course. So this is brief summary of what was done and what we will want to do and what we can do. So these are the light curves which are obtained from monitoring individual images of lensed quasars, and there is a big sort of the database of the light curves. Maybe I'll show it later, so we don't go to this website, but this website contains publicly released data for at least 20 lenses. I think it's maybe 2022, but it's about 20 lenses which were monitored during this CosmoGrail campaign, and there are some other additional campaigns which you can find there, but they released the data, so the data is available. And this is the example of the lens, SDSSJ 1001, that's the name, and you zoom into this little image and you see that this is double quasar image A and B with the galaxies which cause the lensing effect. And then over this campaign, 20 years, the project collected the data, so the light curve from image A and image B, and these are the two light curves are shifted, so they kind of look similar, right? When you look at the top curve and the bottom curve, they look similar. In this case, they were shifted by 119.3 days, which would be time delay between the light curves. So we model this gravitational time delay, and it's described in these two papers, which I gave references there. But the main thing is, this is for statisticians, my one statistic slide, I think. So we define the model where we have the parameters, and so the y and x are the light curves of A and B image. T is time and delta is shift in time. So we assume that we have this one light curve which is shifted by delta t to the other light curves. Then there is also the magnitude shift. So not the two light curves don't have the same intensity. So you have to sort of adjust. So this is the theta zero parameter. And then the additional complication in this is that there is a microlensing effect, which happens when the star in the lensed galaxy crosses the image, or crosses one of those caustics, but changes the properties of the lens, I would say. And we measure the microlensing by this additional term where we have the polynomial expansion. So there is the theta is this intensity of different polynomials, and then T delta is the time delay, which we use to combine light curves. So we assume that the two light curves are the same. I mean, sorry, the two light curves represent the same process, continuous process, and we can put light curves together, knowing the shift between the two light curves, and the shift is due to these parameters which are combined there. And then we assume that this light curve is continuous light curve is generated by stochastic process. In CHASC approach, this was assumed to be random walk process, and Antoine Meyer included the karma process, which is continuous autoregression moving average process, and was used to solve for these parameters. So this is, Bayesian, hierarchical Bayesian model with the likelihoods and all the parameters which we wanted to.
Can I ask a question?
Yes, yeah.
Pardon me if I
Yeah.
myself, but yeah, try to.
Yeah.
Why go to karma? I mean, you were using for you, and it's working wonderfully.
No, yes, maybe, but the problem is that OU is not exactly the process which is associated with variability of quasars, as been known. I mean, Brandon Kelly proposed this as a process which could describe the variability in optical variability in quasars, but when you start looking at the shorter timescales, the OU process is it doesn't reproduce exactly the variability.
Aneta, can you repeat the questions? On Zoom, we can't really hear the question.
Oh, okay. Vinay was asking why karma, not OU, and why did we move to karma? So yes, the OU as the first approximation was okay, but if you go deeper and look at the process, you see that there is variability in the Kepler light curves, for example, where you have no explanation of the this is the PDS higher frequency changes in that light curve. So you have to basically go away and figure out what model can describe this variability. And karma, which Brandon Kelly developed a few years later, is more flexible and can model the stochastic variations in AGN,
Karma is extremely flexible.
Yes, extremely. So if we are not interested in the parameters of karma itself, but using it to describe, in this case, parameter of interest, which is time delay, then I would say that's a good process. And as it was shown recently by Gordon Richards, the karma actually can be used in the large number of quasars and produce nice description of the light curves and the variability. Depending, and I think he has actually, I didn't prepare this here, but he has the study where he uses different orders of karma and finds out which are more likely to be the ones for describing quasar variability. We have more data now. I mean, this is SDSS and variability of quasars. Number of points in the light curves is growing, so there is more data.
At the time scale where you find the usual time delays, the OU process is still okay, or is it only a
you will see, because we compared actually in Antoine's paper, there is a comparison between the two. So it's not. Tak, is it you?
Oh, so OU is a special case of karma. So by just studying karma, basically you're also studying OU, and it is a selection problem, model selection.
Yeah, very good. Thank you, Tak.
I have a question which I wanted to ask a long time ago, even when I was writing article, but I didn't because I didn't want to create a complication. This model with a simple shift delta obviously make the modeling much easier, but it is from theory, is this approximation, or could some delays itself change over the time? So is there some nonlinear facts, over the time? Is it or that's good enough? I mean, anyway.
This is very interesting question. So the question Johnny asked is about how good this model with just time shift, time delay is in explanation of this process. I mean, of the data and the whole process, right? So there are secondary effects because the light travels through the universe, and you have the dark matter. I don't know if you heard recently. There are effects of dark matter which is distributed along the universe, and depending on the path of the light, you go through different parts of the universe. So there is a very small signal, perhaps, but it's possible to, with precise measurements and precise modeling, to look at the traveling of the light and look at the dark matter distribution.
But what would that change here? Is it like has a delta itself as a function of a t, or
I don't know. I don't know.
Maybe there's an attenuation of a t itself.
That's a good question. I don't know. Maybe somebody knows what to say.
Yeah, my understanding is that time delay may depend on time because we are moving and lens might be moving and source might be moving, so angle might change a little. That will affect the difference between difference in time delay over time. But the time scale of those movements might be too large, so we may not be actually capture the change of the time delay as a function of time. That's my understanding.
Yeah, that's actually, the time scales.
Right. But in addition, there's another possibility. In some cases, for the model of the lens source is a jet at the center of an AGN that may be the pointing of the jet may be variable in time, and it sort of sweeps around and so on. So it's possible that there can be short-term variability in the source itself, which gives rise to slightly different paths and slightly different delays. So you have to be aware of possibilities at both parts of the lens, the source and the lens.
That's right. Yeah. Thank you.
Thank you.
Yeah. Okay. So here is an example of from Antoine's paper, the model which was applied to double lens system, this HS2209, and the data were taken from Cosmograil. So this is on the left panel, we have the two light curves from A and B component, and the microlensing across is like the model which was used. The middle panel shows the two light curves shifted on top, and the third panel is the mean prediction for this system. So that's the illustrative of the model. And then this is the comparison between two different solutions of karma, different, so yeah, this is TD karma 2, 1, 3. This is the order of the polynomial in the brackets. So you have two realizations and comparison of the error bars between this. Oh, this is different system than I was showing, sorry. But there is you can see that the uncertainties are much smaller in our case than the uncertainties in the other modeling, which was done in the past by Kumar, and they used the shift of there is a method which is different than our method. It's called Python shift, but it's not exactly what we have here. They don't model the light curve as a process. Okay, and this is the comparison of different lenses which were modeled and the solutions and comparison between two different types of karma process and the existing solutions in the literature. And as you can see, the uncertainties in Antoine's modeling are much smaller than the uncertainties presented in the literature, which is kind of interesting because depending on uncertainties in your time delay, you can determine the Hubble constant in a better way or more precisely. I'm moving backwards. Okay, so if you want to hear everything about TD Karma, I just posted here the link to CFA talk at CFA, which was given by Antoine last summer, and he described the whole model and all the details of the paper. So I put the link, and people can just listen to half-an-hour presentation by Antoine, which is very good, and goes into some statistical details, which I didn't. And I wanted just to spend a couple minutes on this extension, some future project which can be taken, and time delays for a complete set of available lensed images, because those are available. There is Cosmograil data which are public, and it will be nice to apply this model to those lenses. I should say that there are quadruple lenses, which I don't think we touched, and there will be slightly different. I don't know, Tag, did you do any of the quadruple lenses in the past?
So what we do is to analyze each pair of full length light curves. I don't think we have analyzed all of the 4 light curves in one single model. We just analyzed 2 at a time.
Yeah, that's what I was thinking, that it was the quadruple lenses may require a little bit more statistical thinking, to see what's there. What?
Yeah.
Oh, Jeff, do you want to ask a question?
No, sorry, I just left my hand up from last time. Sorry.
Oh, okay. Okay. So this is what I have this unresolved light curves in gravitational lens system. This is something which this is different. Here. Okay. So there is a problem where which was pointed out a while ago by Anya Barnacka and Teddy Chang in these 2 papers, that in some light curves, the high, this is gamma ray light curves, you can see the flare and then you can see the echo of the flare, so delay. And I don't know if it's visible, but this is one of the systems observed by Fermi, where you have pre-flare plus delay, pre-flare, delay. So in the light curves, you have sort of like the cyclic occurrence of the variability. And this has been modeled by autocorrelation function, looking at the lags between first flare and the delay, and the second flare and delay, and third flare and delay. So this is interesting because this is not directly linked to gravitational lensing, but may perhaps to the physics of the source, because here we're looking at the light curves, which are I mean, you have unresolved system, but you have the response between the first flare and the second and the delay. So there is the information about the structure itself in the gamma rays, and probably related to jet. So this was only autocorrelation functions.
I would like to comment a little more about that if I could, because it's really an interesting problem mathematically, because it's much harder for people who like hard problems, because the source is unresolved. You don't have multiple images, so you can't do cross correlation analysis or anything like that. And cases like this, where you can almost see the delays in the light curve, are not, they're sort of the best cases. There are lots of cases where things are much more complicated. So it's a much more difficult kind of inverse problem that there's some literature on, and the paper by Bernacca that you reference here has some ideas for doing that, and there's some other work too. But I think it's a current research problem that I'm working on with some of the Fermi people to get good methods for detecting and then characterizing delays where you don't have a spatial resolution of the source. So everything is kind of mixed together in one light curve, and the idea is to separate them out using things other than the autocorrelation. The autocorrelation is one thing you can use, but there are other ideas. So if any, I don't know if there are any students in the audience there that might be interested in hard inverse problems. This might be a nice one. So anyway,
yeah,
thanks.
Thank you. That's nice advertisement, and good to know, Jeff, that you're working on the problem. That's nice. So this is also another extension was looking at the stochastic variability in multi-band time series, which is something which TAC already tackled in this paper from 2020, where you're looking at two-lensed images and the light curves in two different bands. So you have sort of the spectral information to put this together. And in this approximation, there was just a dumb random walk. So OU process, not karma, which could be nice to use. And meta-analysis. This is something which I just found like two weeks ago when I looked at TAC's paper on AstroPH, where TAC just puts all the lenses together, forgets about the modeling of the lens details, but looking at the time series only and time delays, and trying to get through cosmology to get the basically the Hubble constant constraints. So this is meta-analysis, and it's interesting, and I hope TAC will talk about it at some point here, because it will be nice to see, and maybe try to do with bigger lenses which we will use.
How many data points how many
in the meta-analysis? TAC, how many data points did you use? How many lenses?
So in realistic data, I only analyze 3 lenses. One is double lens, and the other 2 are quad lens. So essentially 7 observations in the meta-analysis.
Mm-hmm.
But after posting this archive, the TD karma, the TD cost, how to say? So the people who are doing time like cosmography, like holy cow people, actually contacted me to work together to analyze their 6 lenses using this method. So probably in the future, I will have something to talk about.
Oh, very good. That's
so
nice.
Finally, 10 years after the mainstream people contact me.
Yeah, no, that's very nice. And I think this, your method, so this meta-analysis could be interesting also as a start maybe for machine learning approach to this, right?
Well, the reason I'm asking is it sounds like not enough for ChatGPT to work yet.
Oh, not yet, but it will be. So, the question is what happens when you have thousands of lenses and how do you combine the information from thousands of lenses to derive the interesting parameters. So this was my last slide at this point. Yeah, meta-analysis. So use all available data. So this has some future projects. I did not mention any reverberation projects, which there are. And if somebody is interested in reverberation between continuum and the lines, there are also those. And some of very recent paper used those to constrain Hubble constant when you look at the high redshift systems and variability there. So, questions? Oh. Yeah, exactly. I see if I can actually stop sharing.
Can also mute there
for a moment. So if there are any questions over here.
I have a comment. If I could.
Go ahead, Jeff.
Your last bullet kind of triggered something in me, the concept of meta-analysis. Can you hear me?
Just a moment. Can you mute and lower the volume down to 0? And when you speak, just sorry, go ahead, Jeff. Now it should be good.
Oh, can you hear me okay?
Yes. Yeah.
Okay, I just wanted to comment on meta-analysis. It's in a different context. Meta-analysis is used in medical studies, a lot, clinical studies, and combining various individual clinical studies, which are small because they're expensive, and using statistical ways to combine the various studies. And they call that meta-analysis. And I think you're using the term in the same sense here. In the medical studies, there's a horrible problem with publication bias, because it turns out that medical journals typically don't publish the results of clinical studies that don't get a result, so to speak. And it's amazing that that's built into their editorial policy. So I once did a study of that, and it's a really bad problem, partially because there's a formula that was developed, I believe, by a psychologist who I think may have been at Harvard back in the 50s, who generated a formula that supposedly tested for whether publication bias was a problem. And that formula is completely wrong, but it's been used to justify meta-analysis in medical studies, and led to a lot of really bad things in the issue of testing for drugs, to whether they can be on the market and are safe and so on. So anyway, it's a tangent, but if there's any related issue where you're collecting together data, but some data that should have been in your sample, but it has been eliminated because of some biased reason, then that can be a problem. So anyway, sorry for the rant, but the term meta-analysis just triggers some really bad memories of how that corrupted a lot of medical studies in the past. So.
But that's not a problem here, is it? Because you can analyze all the lenses, the data that you have. There's no selection process either.
Oh, yeah, we use, so I don't know, I can.
Go ahead.
So in the data which are presented, right, you use all the data points available. So in the meta, yeah.
Because you have studies. If you are not successful, so they just vary.
Right.
Right. But here, like.
You have
The startup community has no such bad habit, like you don't subscribe to any study.
No, Probably not. I don't know. There is the referee.
I think we're a little more subtle.
Yeah, the referee.
We select what we observe, right?
Yeah.
Because this one is bright enough, we'll look at it, and this one is not bright enough, we'll not look at it.
Okay, that's.
And so the data collection is already biased.
Yeah. Okay.
Yeah.
So, okay.
Like a Chandra proposal for something that doesn't seem likely isn't going to be accepted. And so I don't think it's going to be exactly the same effect, but it's also
There is
something to
some.
worry about.
That's right.
But that's another problem unique to the meta-analysis.
I know.
In my amplified effect.
Right.
It's doing single ones where you suffer them.
Yes. But then when you write your single paper, at least you knew how you selected it. And you do meta-analysis for 15 papers that other people have written.
I
So
see.
you may not carry through how that was actually selected in the first place.
I see. You don't know the reasons.
Or even if you write, because the reasons are in some cases they are random. Like you write a proposal to get something observed, and then the TAC says, "Oh no, I think that's not going to have enough signal, so we reject this." And you'll never know what other proposals have been
Rejected.
but have been rejected. What data hasn't been taken.
Okay. It's interesting. It's not an application bias. It's more like
I think it's more an observation.
Observational
it's also more like a grand submission bias.
Yeah.
Granting because you can say, I don't see that problem. Yeah, I see what you mean. Well, but on the other hand, we always make judgment, right? Some judgments are correct. We can't possibly say let's do everything, right?
No.
So the question is where you draw the.
But projects like LSST, for example, are going to be a lot better in that because that's going to survey all of the sky that's visible. And then you'll know that bright things are easier to observe and faint things are harder to observe, but you're not going to get, we observe this one, but not that one for I don't know, this one starts as an L and this one starts as an X, and I like things that are early in the alphabet or something, but you're going to get like a more unbiased sample of what happens on the sky.
Yeah, the same with SDSS to some extent. Yeah, because there is the SDSS is the northern sky, and you have these sources from all.
But whenever you have things like Hubble or Chandra, you select what you believe to be most interesting based on some prior knowledge or some prior observation. And so, you have selection bias by looking at the most interesting bits.
Yeah.
Oh, Casey. All right. Casey, set.
Oh, hi.
Oh,
Yeah, I had a question on, can you hear me?
Yeah.
You can hear me? Yeah.
Yes.
So one question is, how do you know that your method is actually better, right? If just because you get a more precise error bar doesn't actually mean that you are getting a better estimate of the truth, nor does agreeing with previous estimates actually mean you're doing well either. So my question is, how do you test whether or not your time delay method is actually getting a better estimate in some sense?
So that was done by simulations, right? We had simulated light curves where you compare the results with one method and the other method. And so one modification which I didn't say here was that Antoine also improved the computational part of the approach. So he changed the MCMC code and started using nested sampling to look at the multi-mode solutions, which is improvement over TAC. I mean, with a TAC method, we had a lot of issue with the multi-modality, right? Yeah. You had the broadness. Here, the multimodality is sort of dealt with using the nested sampling approach, and it's faster as well. So in that sense, I think the current method is better and it's more sort of ready for the others to use, in the sense that it's fast enough, right? Because the other one was really complex and long. Slow.
Right. So are you testing like within the model? So you're actually simulating from the model that you're fitting, right? You're choosing a karma PQ process.
Yeah.
And then choosing a third order polynomial.
Yeah. So there were simulations like this, but also Antoine was fitting to challenge data sets. So the data which were provided by the time delay challenge in 2016, right? 2016. So he was fitting this data. So you had a comparison to the other methods which were described in that and used in the challenge. And, he had, I don't know if that's in the paper actually, but he has the comparison to the exact data sets from the challenge.
Okay. So, I mean, I was thinking that, it'd be more realistic to test against, say, how can I, it's not good phrase for this, but say, for example, instead of simulating from particular parameters of your model, so the truth is within your model, what you could do is you could take quasars which are not lensed, right? There must be plenty of those where you have time series of unlensed quasars. Use that as the true light curve for which to simulate lens quasar time series. And then for the microlensing, instead of choosing a cubic polynomial, a more realistic thing would have a model that simulates, stars passing through your lens, a more physically based microlensing model, and produce simulations that way. And those would be more realistic. And then you would test your karma plus cubic polynomial against that. And that, I don't know, it would be a more realistic way of assessing the error of your estimator.
That's a very good idea, Casey. No, that's actually a good idea because there is, a lot of quasars, as you said. So there are variable quasars, and Gordon Richards has actually, I don't know if he's got the light curves which we could use, but there are light curves available for quasars.
Right, and they wouldn't require you to assume that they are from the karma process.
Right. So yeah, the ones I'm thinking about were fitted by that process, right? So you've got the models which were applied to the light curves directly, the quasar light curves. We did not, in the optical, with one of the students, we applied karma to the Fermi light curves, but not to the optical light curves. This was with Brandon's code and Brandon's approach, but this one is faster. Basically, that's where you can. I think it's feasible to do this experiment and do the simulations this way. That would be a very good project if somebody wants to take it on. Yeah. All right.
Thanks.
Question. Oh, Axel. Axel's question. Okay. Oh, I'm muting. Sorry.
Go ahead. So it's just a very general question. So what about the dispersion effect? So, I think you already mentioned, like CHASC method where you measure the time delays depending on wavelength, right, or energy. And my question is just like, where have these kinds of measurements been used already, right? And what physics is it? I know, for example, for pulsars, this is done, right, to trace, for example, the interstellar medium, and just see like, okay, what's between your source and the observer, by looking at like how much the profile broadens, right? Yeah. Because the time delay depends on the wavelength.
Time delay should not depend on. Which time delay?
Yes, it does.
Which time? Gravitational time delay.
No, gravitational time delay probably not. I guess. But there are probably other effects, like like in the intergalactic medium.
Yeah, so also in the data itself, the effects, right? So I have to unmute. So if you look at the data and the light curves itself, so when you analyze the data, you account for this absorption effects, or the interstellar medium effects. So they usually are the Redden fluxes. So that is taken into account, and there is a systematic error probably attached to it as well. So there are measurements with these errors, but it's as good as you can do. And of course, when you take photometric measurements and look at the image, of the lens, you assume certain scale at which you extract the light curve photometric measurement, right? So there are all effects related to that measurement.
In fast radio bursts, the delta T depends on the wavelength. Because it travels through the ISF.
Yeah, because
travels
there's
through a vacuum.
That's radio.
that's radio,
Yeah,
it's
that's
different.
right.
That's
But in
radio.
principle, the same thing should apply between infrared and optical.
Yeah.
It's just a question of the time scales on which that
Probably
matters.
small,
Impact
yeah.
goes to what we observe. I
Well,
suspect they're not, but I suspect we're off by 5 orders of magnitude or something like that. But
Yeah, because it's a shorter wavelength, so it's a different effect.
yeah, also we don't
perhaps.
observe on the same scale. Like
No.
in radio, you observe on
Nanoscales.
you sample on milliseconds or nanoseconds, but this you sample on days.
Yeah. Yeah, so those effects are interesting. And leading.
Related to this, so what's the gain then of looking at the bands at the same time? Like with CHASC new method that you so what's the
Well, you've got more data basically, more information, right? I mean, if there is a delay between the bands, which intrinsically might be related to the source itself, because when you look at the structure of the source, the different band is emitted by different part of the AGN, let's say. So you can have a certain wavelength closer to the black hole and other wavelengths farther out. So there could be a difference in just the time delays, or I don't know, there is additional uncertainty on that, where they're coming from. But I don't, yeah, that's a good question how this would.
That's kind of two parameters.
Yeah,
one is
yeah.
the delta T that comes from having the different
Right,
lenses,
and then,
one is the delta R that comes from the radius from the illuminated
Right,
source.
right.
But should be the same in every lens.
Yes, that's
And
right.
the other
because-
one depends on the lens and one depends on the wavelengths, but they're separate. So you have like a two-dimensional parameter.
Right. So there is, of course, this is what Dan Schwartz is trying to do, is to find the scale in which certain different wavelengths are emitted, right? So you can have a lens in radio and lens in optical, and the radio emission will come from different parts of the system than the optical emission. So by looking at exact location of the images, you can determine, and the time delays, you can determine the position of radio emission versus optical emission, which is like gravitational telescope, it's called. So there is a project which Dan is leading, and maybe he will talk about it, because there are a lot of questions on the precise position of each lens, and how do you get this astrometry precisely to measure these shifts. That's very interesting problem as well.
Well, it is time to bring Chuck back. I haven't heard it in talk for a while. So.
Yes, that's right. That will be good. I think I need to eat.
Yes.
Any questions?
You eat, but they can answer.
Yeah, okay. Yeah, they can.
Actually, can I have one comment? I noticed that Yang is here too. So
oh, Yang is
there is time delay that we can look at in flares also. Of course.
Oh, this is huge. This is like the. Okay. Thank you.
There we go. Yeah, actually, that was just a comment. I didn't really have anything more to say other than we are going to see time delays in flares too. So. Any other questions, comments?
Do you want to elaborate on that? Or
sorry, what?
Do you want to elaborate on the time delay in flares, or we can talk about it in a different time?
It's just that when you have a flaring plasma, which changes temperature, it shows it behaves differently in different pass bands. So it's not a it's not a it's not gravitational. It's just related to what the plasma is doing. the cooling time scale. So it's
Mhm.
you can usually tell when something has cooled versus something is heating, because which filter shows first and goes away next and so on. But we can talk about this later too.
Sounds good.
Anything else? Any other questions?
Should we talk a little bit about last week's project?
We can do that, but let me turn off the recording here and say bye-bye to everyone, unless they want to stick around. To
What else is there? Beyond there.
Young is there.
Oh, David's there.
And Casey.
Okay.